So after watching Friday's video, I didn't have you, well, not Friday, last week's third video. I didn't have you do anything because I didn't want you to, but I just wanted you to kind of take it in. So we're going to look at the disk method. The whole idea of the disk method is that we're going to take some kind of function and we're going to rotate it around the x-axis. And when we do that, it's going to create a solid. Now we can look at that solid as a solid piece, or we can look at it as a bunch of disks that are put together, because a disk is essentially a really flat, wide cylinder. But we know how to get the area of a cylinder. That's something that, or excuse me, the volume. That's something that we know, that's a formula we know. We don't know the formula for these other things. But just like we've done with all integrations, if we start with some shape that we know, and then we decrease the width of it, an infinite amount, like for instance on these discs, they're going to be stacked together of different radiuses, and the width will just keep decreasing and decreasing, like it would originally be steps, and then it's going to become a smooth curve. So the function I want to look at right now is y equals the square root of sine x. And I don't really know what that looks like, but I can graph it out. I know that the sine function is 0 at 0, so the square root of 0 is still 0. So it is crossing right here. At pi over 2, the sine function reaches 1, and the square root of 1 is 1, so this still reaches 1. The difference is, instead of, I don't know, the difference is how it curves, but as far as graphing goes, we don't have to worry about that. Alright, and then the sine function comes back down to 0 when it hits pi, and once again the square root of 0 is still 0, so this is coming back down like this. There we go. So, if I want to know, I want this solid to revolve around the x-axis between 0 and pi. So it's going to go like this. It's going to revolve. And it's gonna mimic that shape on the other side. And it's going to be kind of 3D. So I'm going to do my best to kind of, right? Because it's 3D. I know that's a terrible 3D representation, but hopefully you're getting the point. But if we wanted to look at one of these little cross sections, let's say from, let's look like right here. Okay? Right here. This is like our A value. And then this is our B value. And it's creating a little cylinder. Or a little disc. So this isn't, so that's what we call it the disk method. And you could see that that cylinder would come like right here. And essentially this whole piece can be broken up into these cylinders. Like it could just be a bunch of little cylinders or discs stacked together. So when we look at this, we try and do like the volume of a cylinder is the volume of the flat, pi r squared because it's a circle, times the height. So if we look at this, we're getting pi r squared. The radius is going to be figured out by using the function, because like the radius here is the value of the function. So pi, the value of the function, square root of sine x, pi r squared, okay? And then the height, or in this case, because the discs are turned sideways, the width is determined by that delta x. Like this little piece, this little piece. So right now this cylinder is delta x. And essentially this cylinder would be like little steps. But eventually, as delta x gets infinitely smaller, we know that it's going to approach 0, and then just like when we did the area under the curve, it's going to do the same exact thing. So pi r squared h, or height, this is delta x. And how do we get the volume here? We integrate it. So we're going to integrate it from 0 to pi. The reason I pulled the pi out front is because the pi is essentially a constant, so mathematically it wouldn't make a difference here. But yeah, this is all we have to do to get this. Now, this is just the first one we've done, but we're going to look at one that we could actually prove a little bit better. Anyhow. All right. So let's simplify. That's the square root of sine x squared. The square root and the square will cancel out. So this is actually equal to v equals pi from 0 to pi sine x dx. And then, of course, we just do the integration. And the integral of sine x is negative cosine x from 0 to pi. And that's about it. Now all we do is plug in our values, and then we'll have this figured out. So, sorry, oops. All right, so pi, I'm going to plug in pi. So cosine of pi, the cosine function goes 1, 0, negative 1, 0, 1. So at pi it should be negative 1, but since this is negative cosine x, it's actually positive 1. What is the cosine function at 0? Well, at 0, the cosine function is also, let's see, when we plug in 0, we get cosine of 0 is 1, but that's negative 1, so 1 minus negative 1. That becomes 1 plus 1 times pi. This is going to equal 2 pi. Now, we don't really have much of a way to verify that because that's not one that like you've seen before. But essentially, well, obviously, well, it's correct, but I know, like I said, we don't really have a way to prove it. But, so what we're looking for as far as your formula go, volume equals pi r squared. Your radius squared is going to be your f of x squared dx. So that's kind of your general formula for how to do this. And then of course you have to give your bounds. Let's look at one that we know a little bit better. So let's go with a semicircle. No, you know what? Forget a semicircle. Let's go with a straight line. So a straight line, if we rotate it, should form a cone. And once again, a cone is something that we know we have a formula for. So we're going to figure this one out two ways. We're going to figure it out by using the calculus and by using the plane geometric formula. So, I don't know. Let's just make this one up. So, this is y equals 1/2 x. Right? The slope is 1/2. Okay? You see it? This point is 4, 2. All right, anyhow, so y equals 1/2 x. If you rotate it from 0 to 4, you will see it should form a very nice, a very perfect cone. Right? Are you seeing the cone? I know sometimes it's difficult to visualize it in 3 dimensions. But yeah, so it's going to form a cone. So let's do this. Let's do this using the calculus first. All right, so volume equals pi. We're going to go from 0 to 4. And the radius is going to be the 1/2 x squared dx. All right, let's figure this out. 1/2 x squared, that's going to be 1/4 x squared once we kind of square the whole thing. So the 1/4 will come out front, so I'll do it in 2 steps. From 0 to 4, 1/4 x squared dx. Okay, so I squared it, I got the 1/4, and then I pulled the 1/4 out front with the pi because it was a constant. All right, now I can do the integral. This one's actually pretty easy. Volume equals 1/4 pi from, x squared, I'm going to increase that to 3, and I'm going to multiply by 1/3. 1/3 x cubed from 0 to 4. All right, let's do the calculations here. So 1/4 pi, let's plug in 4. 4 cubed, 4 times 4 times 4 is 64. Times 1/3, that's going to be 64 thirds. Mine is 0 cubed, of course, is 0 times 1/3 is still just 0. All right, well, let's just simplify that. So 1/4 times 64 over 3, the 4 and the 64, because obviously when you subtract, it's just 64 thirds. The 4 and the 64 will reduce a little bit. This ends up being 16 pi over 3 once all is said and done. So I'd like to look at that now in terms of if you were in just plain old geometry class, how would we figure this out? Well, the formula for volume of a cone is volume equals 1/3 pi r squared height. Well, let's fill all those values in. 1/3 pi, the radius of the base. So this base from here to here has a radius of 2, right? Because it went up to 2. So pi 2 squared. And then the height. The height of this is 1, 2, 3, 4. All right. So if we were just using the plain old formula for a cylinder, it's 1/3 pi r squared height, the r being the radius of the base. And this, of course, is a right angle. Anywho, 2 squared is 4. 4 times 4 is 16. 16 times 1/3 is 16 thirds. You can see this is going to work out to be 16 pi over 3. Same answer. Now, obviously, not all of the solids of revolution that we look at are going to be this nice and work out perfectly like this. We just kind of hope they do. So, that's about it. Anyhow, I'm going to give you 3 to try out. Oh, what I was saying was they're not all perfect. We can't use a geometric formula for all of them, but this was one where we could, so we were able to prove it, which I think hopefully helps you guys make sense of this. All right, on page 428. Go ahead and do number 1. Let's do number 3. Now I'm going to put number 7 on here. Number 7, when you look at it, it's going to be rotated around the y-axis, but we did integration that way. And there's a little rectangle to guide you. This one's exactly the same. You just have to kind of switch. You have to write it in terms of y instead of in terms of x. I think you'll be okay. If you get stuck, please let me know, but I'd really like you to try that one out, and of course the answer's in the back of the book. Send in your answers when you're done, and if you have any questions, let me know. Thanks.